When it comes to outer space, scientists know about one thimbleful against an infinite quantity. The general public knows and understands far less, although both bodies of knowledge are growing quickly all the time. Outer space and the deep sea are simply very, very difficult to study, and not through a lack of effort. When taking massive technological steps forward like James Webb, we're basically putting on a new pair of glasses with a much more powerful prescription. When the Webb telescope turns its infrared eyes on deep saps, it has already made a huge impact on scientific research about the early universe, as well as the public imagination about far-out space objects. However, James Webb, turns out, is better at giving us new questions or definitive answers. Not long after the James Webb Space Telescope began beaming back from outer space its stunning images of planets and nebulae last year, astronomers, though dazzled, had to admit that something was amiss. 8 months later, based in part on what the telescope has revealed, it's beginning to look as if we may need to rethink key features of the origin and development of the universe. Join us as we dig deep into how James Webb just shattered everything we know about the evolution of the early universe. There aren't too many questions bigger than how our universe came into existence. Pondering our origins has captivated scientists, philosophers, and storytellers for millennia, all trying to understand those first precious moments in the beginning, and how humans eventually arrived on the scene too. We often say, if only it were possible to travel back through time to witness the start of everything, we're slowly finding more ways to pull back the curtain and peer into those times. And in a way, traveling back in time is something that astronomers, astrophysicists, and space scientists do every day when they look into space. Light takes time to travel through the vast distances of our universe, so when we see objects that are further away, we are seeing what they were like further back in time. Not surprisingly, things that are further away require more advanced instruments to measure them, and we need clever ways to make sense of the data collected. Around 13.77 billion years ago, our entire visible universe, every atom, every speck of dust, every star, and every galaxy, was crammed into a volume no bigger than a peach with a temperature of over 1 quadrillion degrees. It doesn't really matter whether this value is in Fahrenheit, Celsius, or kelvins. 1 quadrillion degrees by any measurement system is still around. 1 quadrillion degrees, as in very hot. Naturally, all of the matter was in a completely different state. It was a plasma, with all the electrons ripped off of nuclei, like the interior of a lightning bolt or the gas within the sun. Things got cooler after that as the universe expanded. When our cosmos was around 380,000 years old, it cooled enough for electrons to settle onto nuclei, forming the first atoms. The universe then spent hundreds of millions of years as an expanding, cooling gas made up of neutral hydrogen and helium. For all that time, there were no stars, no galaxies, and not much of anything, really, just a bunch of kinda warm gas. Cosmologists rather cheekily call this era the Dark Ages. But not everything was perfect within that gas. Small pockets of slightly higher density than average gas began to grow. With their increased density, those pockets had a stronger gravitational pull, which could help them draw in more gas from surrounding areas. It took time, literally hundreds of millions of years, but eventually some pockets were able to reach the critical threshold necessary to ignite nuclear fusion in their cores. The first stars were born. Cosmologists call this epoch, which happened sometime during the first few 100 million years after the Big Bang, the cosmic dawn. After the first stars awakened, the first galaxies coalesced, along with the first black holes. Astronomers still struggle to understand this transformative epoch because, as of now, we have no direct observations of that time. Ironically, we have direct observations of the moment when the cosmological gas became neutral in the first place, 380,000 years after the Big Bang. That event released an enormous amount of light that remains today in something called the cosmic microwave background, which serves as a baby picture of the universe. And we have direct observations of the present-day universe because it's right around us. But we don't know exactly what went down when the first stars and galaxies appeared. We don't know how big the first stars were, what strange processes led to their formation, or how quickly it all assembled. For years, we only have theory and guesswork. But now, things are changing. We're now in the James Webb era of astronomy, with new secrets and details about the universe being revealed each time it views a novel region of the sky. James Webb, the largest, most powerful observatory ever launched from Earth, was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope's giant segmented mirror and exquisitely sensitive instruments were designed to uncover details of cosmic dawn never before observed. Such observations were supposed to take time. Initial projections estimated the first galaxies would be so small and faint that James Webb would find at best a few intriguingly remote candidates in its pilot investigations. Things didn't quite go as planned. Instead, as soon as the telescope's scientists released its very first images of the distant universe, astronomers such as Rohan Naidu at the Massachusetts Institute of Technology started finding numerous galaxies within them that, in apparent age, size, and luminosity, surpassed all predictions. The competition for discovery was fierce. With each new day, it seemed, claims of yet another record-breaking earliest known galaxy emerged from one research group or another. According to Charlotte Mason, an astrophysicist at the University of Copenhagen, everyone was freaking out. We really weren't expecting this. In the weeks and months following Webb's findings of surprisingly mature, early galaxies, theorists and observers have been scrambling to explain them. Could the bevy of anomalously big and bright early galaxies be illusory? Perhaps because of flaws in analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or just maybe were they the first hints that the universe is more strange and complex than even our boldest theories had supposed? At stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. James Webb's early revelations could rewrite the opening chapters of cosmic history, which concern not only distant epochs and faraway galaxies, but also our own existence here in the familiar Milky Way. As Webb scientist Mark Makarian, a senior advisor for science and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm, but to break it. You just don't know how it will break." According to the Standard Model, which is the basis for essentially all research in the field, there is a fixed and precise sequence of events that followed the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then, the force of gravity pulled together the stars into galaxies. However, the Webb data revealed that some very large galaxies formed really fast, in too short a time, at least according to the Standard Model. Galaxies nearly as massive as the Milky Way and full of mature red stars seem to be dispersed in deep field images obtained by the James Webb Space Telescope during its early observation campaign. And they are giving astronomers a headache. Nobody expected them. They were not supposed to be there, and now nobody can explain how they had formed. This was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Notably, observations preceding those of James Webb were already filling some astronomers with niggling doubts. In 2016, the galaxy GNZ-11 was discovered. According to the established theories, its light would have been emitted 13.4 billion years ago, a mere 400 million years after the supposed origin of the universe. In astronomical terms, 400 million years is but a sigh. In 2020, the oldest black hole yet observed was discovered at 12.8 billion years old. But how could a black hole arise at a time when matter was supposedly as yet too diffuse to cause gravitational collapse? Becky Smethurst, a junior researcher at the University of Oxford and a specialist in black holes, says, "Let's assume the very first stars formed black holes around 200 million years after the Big Bang. After they've collapsed, you've then got about 13.5 billion years to grow your black hole to billions of times the mass of the Sun. That's too short a time to get it that big just with accretion." Again, it was only in 2021 that the galaxy BRI 11335-417 was discovered, a spiral galaxy 12.4 billion years old, about a billion years earlier than the time thought possible to form this type of complex galaxy, according to the Big Bang theory. According to physicist Guillermo Barro of the University of the Pacific, we have discovered mammoths in the universe at a time when it seemed like they shouldn't exist. Now, we need more data to know how they got there. The James Webb Space Telescope promises to shed further light on these questions, but we predict that new data will only create further problems for the proponents of the Big Bang theory. Unfortunately, it was not an isolated incident. There have been other recent occasions in which the evidence behind science's basic understanding of the universe has been found to be alarmingly inconsistent. Take the matter of how fast the universe is expanding. This is a foundational fact in cosmological science, the so-called Hubble constant, yet scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as the sort that the Webb is providing. The other involves measurements of nearby stars in the modern universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better, but the problem has stubbornly persisted even as the data have gotten far more precise, and now new data from the Webb have exacerbated the problem. This trend suggests a flaw in the model, not in the data. Two serious issues with the standard model of cosmology would be concerning enough, but the model has already been patched up numerous times over the past half-century to better conform with the best available data. Alterations that may well be necessary and correct, but which, in light of the problems we are now confronting, could strike a skeptic as a bit too convenient. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution that would have implications far beyond the world of science. Notably, in addition to the two problems, our standard model of cosmology has confronted with another issue. The tendency of matter to clump together in the early universe is inconsistent with how it clumps together today. Known as the sigma-8 or S8 tension, it is like a little brother or sister of the Hubble tension, so it is less significant but worth keeping an eye on. All the problems could signal that scientists are misunderstanding something big about physics, and a recent paper in the journal Physical Review Letters adds to the suspicion that this might be the case, for the S8 tension at least. In the standard model of cosmology, the universe started off almost but not quite uniformly dense. We know that because the oldest light we can see, known as the cosmic microwave background, shows only tiny variations in temperature from one point on the sky to the next, reflecting variations in the density of energy and matter in the cosmos. As the universe expanded, gravity, as described by Einstein's general theory of relativity, amplified those variations to create the huge variations we see today in the form of clusters and superclusters of galaxies. That process is somewhat suppressed, however, by dark energy, the still mysterious force causing the expansion of the universe to accelerate rather than slow down, which pushes matter apart before the density variations can get even greater. In the new paper, scientists argue that this suppression of clustering is too large to explain with the standard model. Not only that, as Robert Caldwell, a cosmologist at Dartmouth College who did not participate in the new study, explains, it seems like the timing of whatever's causing the acceleration is not in synchrony with the effect on the clumpiness. That is to say, the suppression of the growth of the so-called large-scale structure of the universe, the web of galaxies, clusters, and other cosmic structures that are bound by gravity, begins to kick in later than you'd expect to see from dark energy alone. This observation suggests that some theory of gravity other than general relativity might conceivably be at play. As Benjamin Wondelt of the Lagrange Institute in France says, it's a thought-provoking analysis, exciting if true, but changing general relativity is a high price to pay. So is it true? The answer so far is that nobody knows for sure. According to David Weinberg, chair of the astronomy department at The Ohio State University, it's an interesting paper, but I wouldn't say it's a big deal on its own. However, the investigation does fit into a larger set of papers that are maybe finding a discrepancy between the level of matter clustering in the present-day universe compared to what we would predict based on what we observe in the cosmic microwave background. These discrepancies would be small enough to make theorists wary that they might not be significant at all, except that they all tend to point in the same direction, with modern-day density variations below what you'd expect based on the standard model. If they're real, the implications are very profound, because you would probably have to modify the theory of gravity on cosmological scales in order to explain it. And that's not easy to do. To be clear, this kind of change would be different from modified Newtonian dynamics, or MOND, a theory of modified gravity proposed to explain away dark matter. Here, too, the idea of tinkering with general relativity has been tough for astrophysicists to entertain. What might be different in this case is that the authors, Natmin Nguyen, Dragan Huterer, and Yuewei Wen, all at the University of Michigan, didn't set out to solve the problem of the S8 tension. They were interested in whether the history of the universe's expansion was consistent with the history of structure growth. We expected, says Nguyen, lead author of the paper, that they would, in fact, be consistent. When the researchers found this wasn't the case, he adds, they went back and rechecked their analysis to make sure they weren't missing something. But we found that we weren't, Nguyen says. The inconsistency, it turned out, might be explained by some additional force layered on top of gravity and dark energy, a force that would add to the tendency of dark energy to tamp down structure formation. Or it could suggest that dark energy itself became stronger at some point, Caldwell says. That's what excited me about the paper, he adds. Caldwell doesn't consider the paper definitive, though. Joe Dunkley, a physicist at Princeton University, who also wasn't involved with the work, agrees. This is interesting, she says, but to me, it is too soon to say that this shows significant evidence of a problem with the standard model of cosmology. And a few scientists, including David Spergel, former chair of astrophysics at Princeton and now president of the Simons Foundation, think the argument isn't very convincing. The authors ignore recent measurements that are consistent with standard theory, says Spergel, who wasn't part of the study. And as this paper argues, analyses of large-scale structure at nearby distances are probably underestimating the important role that galaxy winds play in driving gas out of galaxies. I'm not sure I would have published this paper. On Spergel's first point, Nguyen agrees that he and his colleagues need to do more research. We're looking into more data sets from new, presumably independent experiments of the same observables, he says. But Nguyen also points out that in the recent measurements that Spergel cites, the latter's team actually references Nguyen and his colleagues' latest work and the idea of tweaking with general relativity as a possible solution to the S8 tension. And, Nguyen argues, the community is still divided over the role of winds in reconciling S8. In short, everyone, including Nguyen and his co-authors, agree that their results are not definitive. According to Nico Hamaus of the Ludwig Maximilian University of Munich in Germany, it's useful to play these exercises. That's exactly how you find loopholes in the models, and if we can really substantiate such things, that really means there's something going on that we don't understand. But even if definitive confirmation comes, the Hubble tension remains, and almost everyone agrees that problem is a much bigger deal. After all, we may be at a point where we need a radical departure from the standard model, one that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time. Last but not least, a new investigation of data collected by NASA's Cassini mission, which ended 6 years ago, has revealed that the spacecraft spotted a key ingredient needed for life on Saturn's icy moon Enceladus. The Cassini observations have revealed a powerful energy source for potential life forms deep below the icy shell of this moon. Enceladus blasts out plumes of ice and water from fissures in its icy shell, and scientists have known for some time that organic molecules, some of which may have the right chemistry to be important for life as we know it, are contained in these jets. In 2017, scientists found carbon dioxide, methane, and hydrogen in Enceladus's plumes, indicative of a metabolic process called methanogenesis. As its name suggests, methanogenesis produces methane, which is widespread here on Earth and could be a sign of life on other worlds. The new confirmation of hydrogen cyanide, a crucial precursor for some molecules that needed to be present on Earth for life to arise, takes the concept that Enceladus could be habitable to a whole new level, however. The same research team also discovered that the subsurface ocean of Enceladus, from which the plumes apparently originate, could be the source of several other organic compounds, some of which serve as fuel sources for terrestrial organisms. This indicates that there may be more energy available for life on Enceladus than was previously thought. As lead author and Harvard University doctoral student Jonah Peter said in a statement, "Our work provides further evidence that Enceladus is host to some of the most important molecules for both creating the building blocks of life and for sustaining that life through metabolic reactions. Not only does Enceladus seem to meet the basic requirements for habitability, we now have an idea about how complex biomolecules could form there and what sort of chemical pathways might be involved. To get started, life as we know it needs compounds like amino acids as its essential building blocks. The team behind the new findings describes hydrogen cyanide as the Swiss Army knife of amino acids because of the variety of ways the molecule can be stacked to help construct amino acids. The discovery of hydrogen cyanide was particularly exciting because it's the starting point for most theories on the origin of life," Peter said. "The more we tried to poke holes in our results by testing alternative models, the stronger the evidence became. Eventually, it became clear that there is no way to match the plume composition without including hydrogen cyanide. This newfound source of chemical energy is more powerful and diverse than the methanogenesis process," study team members said. This means that there are various chemical pathways available for organisms in the moon's subsurface ocean. If methanogenesis is like a small watch battery in terms of energy, then our results suggest the ocean of Enceladus might offer something more akin to a car battery, capable of providing a large amount of energy to any life that might be present, research co-author Kevin Hand, a scientist at NASA's Jet Propulsion Laboratory in Southern California, said in the same statement. The team used statistical analysis to arrive at their results. Armed with the new findings, scientists can now investigate these chemical pathways for life in the lab as they attempt to discover if Enceladus really has the right stuff for life. We used math and statistical modeling to figure out which combination of puzzle pieces best matches the plume composition and makes the most of the data without over-interpreting the limited dataset, Peter said. There are many potential puzzle pieces that can be fit together when trying to match the observed data. The research also demonstrates that the Cassini mission keeps delivering important insights about Saturn and its moons, despite having made a suicide dive into the atmosphere of the gas giant in September 2017. As Cassini team member Tom Nordheim, also of NASA's Jet Propulsion Laboratory, said, "Our study demonstrates that while Cassini's mission has ended, its observations continue to provide us with new insights about Saturn and its moons, including the enigmatic Enceladus." The team's research was published on Thursday in the journal Nature Astronomy. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.